he moved back to Germany to New, and then later he became several years ago a group leader at the Naab for astrophysics in Africa. He's and so for this I let you start your talk.
Thanks a lot, Lucio, for the very nice introduction, and thanks a lot for inviting me here, and also to Pedro for the organization. Where is a wonderful organization? It's really always, I haven't been here for many years, so it's fun. Okay, so I talk about title, yeah, anyway, galaxy simulation resolved ISM clustered star formation, global cluster formation, intermediate mass black hole growth. It's a large range of topics, and I try to explain you how all of this might be connected. First of all, I'd like to highlight that this, all I show here is work of an amazing group of talented young researchers, Natalia Lahen, Christian Partmann, Konstantina Fotopoulos, Jessica Hislop-Chayuhu, and Tim Ratyan, who are working with me, who have the pleasure to work with postdocs or PhD students. So this is all their work, and of course refer to their work in the respective steps. So why clustered star formation? So let me give you a very brief introduction into what is observed, and then take this as a bit of a motivation. You know this, spiral galaxies and stars do not form homogeneously. They form in star formation region in clusters, and here you see H2 regions, clusters. There's new stars emit radiation, and then you have ionized bubbles around them. So this is the normal mode of star formation. It's clustered star formation. Okay, so it seems important to understand how this clustered star formation works. In lower mass galaxies, SMC here, you also see clustered star formation, and there is something up here, globular clusters, whose formation is not yet really understood, but they might have something to do with the clustered star formation in normal galaxies, probably an extreme version of it at very high redshifts, but it's unclear. So the models for globular cluster formations are not very mature yet. So if we go a bit more into detail, if you have a forming star cluster, and here this is a very nice example also in the SMC, you have a group of young stars. These young stars emit radiation. So they form from the dense ISM. They emit radiation. They create H2 regions. They emit stellar winds. The massive stars push out material in winds. Both processes shape the medium around it. And then after some time, they explode as supernova, and probably the whole thing is gone. Okay. And this happens again and again and again, and this is how stars form in the universe, typically. So you see radiation, H2 regions, fancy H2 regions, and you see, stellar wind bubbles. And I talk a bit about the impact of stellar wind, but not so much here. It's very tough numerically to implement stellar wind feedback. And then at the end of the lifetime, this is a bit of a cheat because this is type 1a explosions. They just look nice. But massive stars explode as supernova, and then they expel, they enrich the material, the interstellar medium, and they create a hot phase. So this is a very hot phase. The phase here is like warm 10 to the 4K, but the phase here is like 10 to the 6, 10 to the 7K or more. And there are other fancy things happening probably in these shocks. Cosmic rays are generated, and then they start propagating into the interstellar medium, which I'm not talking about here. This is a different topic, different talk. Now, as a result of all of this, galaxies can develop large-scale outflows. Okay, this is M82, famous galaxy And so the gas is pushed out of the galaxy and enriches the circumgalactic medium with material. We do not really know how these winds are launched. Okay, I think it's at the moment it's unsolved. We have some ideas, but these winds are very important, qualitatively very important for galaxy formation, because if galaxies do not develop these outflows, we would have no spiral galaxies in our universe. I think this is one of the qualitative results of cosmological simulations of the last 25 years or so. Another galaxy with outflows. And here is the kind of consensus of what galaxy formation has been figuring out. This is a dark matter halo mass function, and this is the galaxy mass function. So the black things are the measured ones. And here you see many attempts of cosmological simulations to reproduce this galaxy mass function. And qualitatively, if you put in something like stellar feedback, so you drive gas out of galaxies during their evolution, you reproduce these galaxies, and if you do AGN feedback, you reproduce the massive galaxies. This is well known. It's a qualitative result and has resulted in early successes for the formation of this galaxy. So this is kind of the context. Okay, these outflows are very important to get the morphological mix of galaxies we have, possibly. Okay, now here's a complication, and this is an oversimplification a bit. So cosmological simulations of galaxy simulation, large-scale simulations, have a phase structure in the interstellar medium which looks a bit like this. Okay, many of the big simulations, this is warm diffuse gas, and then there are subgrid models for star formation, subgrid models for wind ejection, and so on and so on. People have been working on this for years. Now the ISM actually looks like this, exactly like this with the same colors. And so you have a dense phase, molecular phase, you have a neutral phase, around it, warm and neutral ionized gas, and then this is embedded in a hot phase. This is a three-phase medium. And with all its observables, okay? So this is wonderful because if you can do this in simulations, you can connect every phase to an observable to actually see whether your simulation does something which is useful or maybe not useful. So H alpha traces star formation, nitrogen, and so H2 regions, dense gas, C+, X-rays, hot gas, CO, molecular gas, gamma rays, cosmic rays, and so on. So there's an observable for all the things you have, which makes it so interesting to me. I don't talk very much about post-processing, but we have done it, and it looks kind of okay. Now, imagine you have a star exploding. Then when the star explodes in a dense medium, the blast wave actually cools away relatively rapidly, and you don't have much impact to it. It's basically, it's a lot of energy, but it's cooled away. It's different if it goes off in the warm medium. It's even more different if it goes off in the hot medium, okay? So you cool much less, you generate much more hot gas if the ambient density of your supernova explosion is lower, okay? Now, you would think, oh, stars are bonded in a dense phase, so they explode, so it's very difficult to do something. It's actually not correct, and I will show you why this is. Now, with a different set of simulation, we have kind of qualitatively tested this, okay? This is a stratified box simulation. So this is a disk in a periodic box. It's a different code. It's a grid code, flash, but we have a gas phase medium here, and then we put in expected supernova explosion rates, okay? In this experiment, we put the supernova at the peak densities. In this experiment, we put half of them at random densities in a scale height. And in this experiment, we randomly distribute them with a given scale height. So you see, when you explode all supernova in the dense phase, you create a two-phase medium. Blue is cold, warm is green. it's only a two-phase medium. It's turbulent, it's two-phase, but there's no hot phase. Okay, only if you manage to explode supernova in a lower density ambient medium at random locations, basically, it's possible to generate supernova bubbles that overlap and sustain a stable hot phase. Okay, now we think, or I think, a stable hot phase is what generates galactic outflows. So you have hot gas. The hot gas is driving the material out. Here is a brief illustration what has plagued galaxy formation forever and is still plaguing galaxy formation. This is an example for the simulation of a single supernova explosion. Now, in a relatively highly resolved medium, this is SPH simulations, gas particles with 100, with 10, and with 1 solar masses. And you inject thermal energy here in a larger region because your resolution is lower, and then here your resolution is higher, and here your resolution is higher. And then you let it evolve. Okay, and this is how it looks like. So if you do it in a low resolution medium, the remnant cools immediately. Nothing happens. Okay, everybody here in this room, I think, has been working on this and knows this pretty well. If you go to higher resolution, you generate a hot phase. You kind of get a shell. Okay, so it looks better, but not perfect. If you go to even higher resolution, you pretty well resolve a set of phase. You have a hot phase, you have a shell, you start seeing some instabilities in the shell. And this is for a single supernova explosion. Okay. So this is, in my view, it's critical that simulations, high resolution simulations resolve this, because then if you do, you don't have to rely on subgrid models for the evolution of this. Okay. And you can imagine that the hot phase properties of a simulation like this and this is very different. Okay. Outflows will be very different, and so on. Yu has written a paper about this with a resolution study and nicely demonstrated this. So the simulations I show you are kind of here in this regime. We work with typically 4 solar mass resolution, so it's not as good as this. It's not as bad as this. So we are kind of here, and we are working towards improving this. Project is called Griffin, if you want to look it up. And here is a very brief overview of what we have in the simulations. In smooth particle hydrodynamic simulations, we typically work with the resolution of a solar mass, few solar masses, 0.1 spatial resolution, parsec spatial resolution. Star formation at high densities I'll talk to you about later. In the latest model, we draw individual stars from a full initial mass function. We realize every massive star. We keep track of its injection properties, radiation, winds, supernova explosion times, enrichment histories. We track the lower mass stars for their contribution to the interstellar radiation field. And then we assume an optically thin approximation. We only do low mass galaxies at low metallicities and hope this is not too crazy. And then locally, we compute the shielding from the interstellar radiation field to be able to do the gas chemistry. So we have a simple network for gas chemistry, H1, H2, CO, H+, and so on. We're not the only ones doing this. Here's an incomplete list of other people doing this as well, and some of them are actually in this room. So photoionization is important. We don't do radiation transfer. We use a relatively simple Sturmgren approach. Radiation transfer would be too costly for the simulations we have at the moment. So what does this look like? This is a 10⁸ baryon dwarf galaxy. And you can see very nicely the gas phase structure. This is a full realization, the stars, dark matter, and so on. I just show the gas phase here. You see cold filaments, you see molecular cloud rings, from individual supernova explosions. Here's a little movie that Yu has made years ago This is the gas phase distribution. This is molecular hydrogen. This is ionized hydrogen. And if you look here, every one of these red dots is a individual supernova explosion. Okay, this is how the simulations qualitatively look like. So relatively high resolution, detailed structure with drive outflows. I don't talk too much about the outflows today. And this is another feature of the simulation. We can actually trace the local interstellar radiation field. And this is as a function of height and as a function of radius. So in star-forming regions, we have very high values of the interstellar radiation field. This is important for the photoelectric heating we have included in the simulations. And this is important for the gas temperature distribution at high densities. Okay, this is part of the simulations here. So we can do this. I just demonstrated as a simple experiment of what we can do here. I mean, this is not, you know, it's a good model, but it's not perfect. But what we can do is we can see whether if we have different physical processes, what is the impact of the different physical processes? And here's an overview of a kind of a parameter study. I don't like parameter studies, but I like this one. Anyway, this is the fiducial simulation. Three-phase medium, structured ISM, turbulent. Everything looks very reasonable. I'll show you later how this looks like. If you don't have photoionization and supernova, you have this, okay? This is not a reasonable interstellar medium, okay? This is wrong. It's two-phase, it has the wrong phase distribution, the wrong structure. And then you can do other experiments, like you can turn off photoionization, you can turn off photoelectric heating, you can turn off both, and so on and so on, and you can do this all the way. I highlight a few examples here, and another one is this one. This is called 3 megayear. So what we did here is we forced every star, every massive star, not to live its full life until the explosion, but to explode after 3 million years, okay? Imagine the time resolution here is very high. We go to time steps of 100 years. That's also why the simulations can be very expensive. And you might wonder, why do you do this? Looks a bit different, but who cares? And this is the reason why we do this. So what I show you here is the distribution, the number of supernova explosions as a function of the ambient density where they explode, okay? So I highlight two simulations, a fiducial simulation and the one where we explode every star after 3 megayears. The fiducial simulation peaks at 10 to the minus 2 or 10 to the minus 1. This means that a typical supernova, even though we form stars at 10 to the 3 particles, typical supernova explodes at 10 to the minus 1. If you have a structured resolved interstellar medium. And that's a big thing, okay? It's a big difference if you consider the impact of supernova explosions. So if, for example, the simulation anyway, it's too complicated. Now, take a look at the magenta line here. And this is where we force every star to explode after 3 million years. So every star cluster has less time to evolve, less ionization, and the stars have less, the stars move, they move out of their birthplaces, okay, and they just have less time to move out of their birthplaces. So these two effects actually result in higher ambient densities at the explosion time, okay? And if you look at the, say, outflow rate here, this results in lower outflow rates by an order of magnitude. So the star formation rate in these two simulations is exactly the same. The outflow rates can be an order of magnitude different depending on how you implement the stellar lifetime distribution of your massive stars. Okay, that's shocking, okay, or great, however you see it. It means that the details of a massive star evolution implementation in your simulation matter for how much outflows you drive and in the end, how this galaxy would evolve cosmologically. This is not the only we have confirmed this with other type of simulations. Other people have confirmed this also with other codes and other types of simulations. So this seems to be a robust result. Okay. And here's just a teaser. We have been able to go to SMC size galaxies. Okay, this is the stellar distribution, gas temperature and pressure. So we can now. This is 10 to the 2 times 10 to the 8 particles simulation. So it's very expensive, but hopefully useful.
You said the formation rate is the same.
Yes.
The outflow rate is very different.
Yes.
That means so on longer time scale, you see an effect on the star formation rate afterwards.
Yeah, in principle, yes, but the star formation rates in these systems are so low that yeah, and the mass loading is very high. You have seen here mass. No, it's sorry, mass loading is not very high, but that's a different issue. But it's a factor of 10. So the star formation rates are very low. Long term, you would see this, and this is a low mass, low metallicity system. We don't know exactly how this could look like for a Milky Way. We cannot do this at the moment. And let me emphasize here that other people go similar approaches with individual star formation. So this is, Uli Scheinweiler has done some work, but also connection with us, Eric Emmerich with ENSO, Anderson with Ramses, Matthew Smith with Arepo, and Thales Gutke also with Arepo. Similar approaches, individual star formation, highly resolved interstellar medium. So I took this slide from Natalia Lahan's review. I think qualitatively, and also to some degree quantitatively, the results are very robust from all these studies. Now, a few words to star formation. So I come from the horrible galaxy evolution. That's not horrible. So this horrible subgrid galaxy, that's my history. The horrible, smooth subgrid, that's what I did like 10, 15 years ago. And then the question is, and then I presented something at a meeting and people told me, look, you can't do this, okay? You cannot use the subgrid models. You cannot go to high resolution, use the subgrid models, the galaxy cosmological people use. It's all wrong. You have to think about something different. And I thought, okay, come on this. But in the end, this person was right. Maybe, let's see. Okay, so here's a little fun experiment. So this is a phase diagram of what we can resolve. Okay, we have a warm phase here, we have a cold phase, we have a hot phase, 3-phase medium. This is the photoionization part here, and here's our star formation regime. Okay, so this is like 8 times the Jeans mass. The Jeans mass is half the Jeans mass. So we started out thinking about, okay, we have a Schmidt type star formation. So star formation is proportional to the density over the free fall time with some efficiency, 0.2%, 2%, 10%, 20%, 50%. We vary this. This is the galaxy formation approach, the traditional galaxy formation approach, which has resulted in reasonable results, reasonable values compared to observations. So we start star formation here with the free fall time delay. And then once we end up here, we actually force the gas particle to form a star, okay? And we have tested different approaches. And you can see here on the right, this is the density distribution of where stars form. If we have a high efficiency, we form stars at relatively low density. So here, if we have 0 here, it doesn't mean 0, it means instantaneous formation. If we have instantaneous formation, this is this line here, we go, basically most of the stars form between 10 to the 3 and 10 to the 4 densities, particles per cubic centimeter. So depending on what year, the initial, the density at birth can be very different, okay? Now, if you look at the density distribution of the supernova explosions, it's very similar. So this doesn't matter for, where a supernova explode and how the ISM is structured in principle. There's an outlier here, which is the red line, and the red line is the one where we have no photoionization. Okay, so we have no process. Once the stars are born, the hot, ionized bubble is generated, the density goes down. This results in an overall higher star formation rate and a distribution of supernova which extends to high densities and also to very low densities. This is due to clustering. So you can imagine a supernova goes off, the next supernova goes off in the bubble of the first. This then has a very low ambient density. So if you repeat this process, you can create very efficient, super bubbles, very efficiently create super bubbles, which drive material out of the interstellar medium. So this is, we thought, okay, this is good. But now, if we track the star clusters, and this is work by Jessica Hislop, if we now track the star clusters and plot them on observed relations, this is the size, surface density, and total surface density, half mass density, and total surface density, a function of cluster mass, you see, it's not great. So the low efficiency values give you very dense clusters, okay? Probably too dense, too small. The high efficiency give you less clusters. Same star formation. It's just a fraction of stars that forming cluster is lower here, but also not great. Okay, not wonderful. And also, the simulation without photoionization gives you more massive clusters. And this, I think, we understand, because if you have a star cluster region forming, if you have a forming star cluster in a collapsing region, and you do not have photoionization, then the gas heats up to 10 to the 4. At some point, you stop the accretion, you stop the formation of stars just by photoionization, H2 region. If you don't have this, more gas can collapse to dense regions, more stars can form until the first supernova explode, which take a few million years, 6, 7, 8 million years, depending on the mass you have. So you form more massive clusters. Everything is more clustered, and you drive more outflows. Okay, it's not great. Okay, so there's a challenge here, which we have not yet solved. We have new models. We have we reach limitations of what we can do for the dynamics of the simulation. Here we have realized every star above 4 solar masses. We now realize stars with a full IMF. And Natalia Lahin has written a paper with indications that this kind of captures the relaxation of the early relaxation of star clusters and the tidal stripping and the mass loss. So then they expand. So this is going in the right direction, but there is a problem here still. Okay, now this is what I started with when I did astrophysics, merge galaxies together. We did it. Natalia Lahin did it. 2 dwarfs, very high resolution, merging together. Okay, a huge starburst and lots of clusters. Okay, and lots of massive clusters. So this is the starburst. It's like a 10 to 100 times higher than the typical star formation rate in the idealized system. And it's very structured, a lot of cold gas. And Konstantina has analyzed the cold cloud structure. So this is cold, lower than 300 Kelvin structures, analyzed and extracted. And here's a mass function, cold cloud mass function, which roughly follows the observed minus 1.8. This is at different times, okay, in the simulation. So we do form cold clouds with a mass function, which is kind of observed. Some people say, oh, this is trivial, this is gravity collapse, turbulent collapse, whatever. Still, I don't think it has to be this way. Now, here's the mass function, and if we do it at different densities, you see the slope of the mass functions at different times stays the same. So we even have internal structure in the clouds, which seems to be self-similar. Okay, yes.
Is mass function dependent on the subject molecule?
We haven't tested this because this simulation took 4 months, and it's not good for parameter studies. It's a good point, but you know, we thought about it, but then we didn't want to spend computing time on yeah.
Is this where you don't like parameter studies? Was there another reason?
Why would I not like Ramses studies?
Parameter studies.
Parameter Ramses. No, I like parameter studies. That was a bad joke, of course. But I think some parameter studies are, I don't know. They're parameter studies and they're parameter studies. Let's put it this way. But here it's very tough. We can do it for isolated systems. That's what I showed you before. Because the simulations are faster, but in the complex starburst situation, it's much more difficult to do this. Now, Natalia here has looked at the star clusters, okay? So she has identified all the star clusters forming in the simulation and plot the star cluster mass function as a function of time. This is this one. -2 is here. So the star cluster mass function looks good, okay? So we have a cloud mass function which looks reasonable. Out of the clouds form star clusters which look reasonable, okay? I would say this is promising. This is at least not discouraging. Whether we have the normalization right is another question, because this is the question of how many clusters do you form, how many stars do you form in clusters versus field? Okay, this can vary. I skip this. And here's the star formation rate of this first encounter, second encounter, and this is the cluster formation rate. Okay, so with higher star formation rate, we form more stars in clusters. It's probably observed, but there's a lot of discussion in the observational cluster formation community.
So, sorry, are these globular clusters?
I answer this in the next slides. Okay. So we have a few very massive clusters, up to 10 to the 6 solar masses. And here's how they form. So we have a first cluster forming here. Then we have a second massive cluster forming a bit later. And then we have a third massive cluster forming in the supershell created by the supernova explosions from the first cluster here. Okay. Now, these objects are interesting. And I show you the formation of the most massive cluster in the simulation, the one in the supershell. It will form here. And this is a movie which only takes like 50 million years. Okay, it's very short. Density, temperature, pressure, photoionization, supernova explosions. So the shell comes in here. We start forming little photoclusters and more of them. The shell gets denser and we form more of them. The shell gets denser and much colder. So you see the rapid hierarchical assembly of a very massive star cluster. Okay? We have two progenitors here. These merge. And by this time, basically, supernova kick in, and all of the cold gas is gone. And the formation of this cluster is over. Okay? And this is, what is it, 10, 15 million years in total. Okay? This cluster has a mass of 10 to the 6 solar masses. This is what we can do at the moment. I mean, there are a lot of complications here, but it has a mass of 10 to the 6 solar masses, and we realize all stars down to 4 solar masses here. We have now better simulations, but this is what we have. If you look at the density profile of this cluster and its three massive friends in the simulation, and you compare it to globular cluster, present day global, it's not a very fair comparison, okay? There's billions of years of evolution between. But we have a flat core, we have a profile which very well looks like could be, globular cluster profile. And also the global properties, dispersion, half mass radius, surface density, if you plot them on the plane of globular clusters, they look pretty reasonable, okay? And here's how the cluster actually evolves. So this is the gas, the solid lines is gas, sorry, the dashed lines is gas density, okay? And you see the gas density doesn't become very high in the center, but you pile up, you form stars and you pile up stars, okay? You pile them up to very high densities, 10 to the 6 particles. This is solar masses per square, per cubic parsec, 10 to the 6. And then you have a rapid onset of relaxation, okay? So in the center. Now, caveats here, the second order leapfrog, dynamical integration, okay? So you cannot trust the simulation for very long. I mean, there are different ways of phrasing this. Either you don't trust it at all, or you say you don't trust it for very long because you don't capture all the relevant effects, but we try to overcome this in the future. Now, another interesting part of this is the hierarchical formation of this thing makes the cluster rotate. And if we compare the rotation, let's see, this is velocity and this is dispersion. So the structure, of course, is okay. It's a self-gravitating system to observed Gaia clusters. And this is rotation. It looks good, okay? The rotation looks good. The structure looks good. Everything looks okay. I mean, the dispersion is not so surprising. Rotation is more surprising, actually. Now, for this starburst, Natalia has done a post-processing with SCIRT, which is very nice and beautiful. You see all these star clusters, dust. You see this shell here. It's a low metallicity system, so there's not a lot of dust. You can do all kinds of star clusters, experiments with this, and Natalia has very nicely done this in her work. And you can create an SED and compare it to observed dwarf starburst SEDs, which looks surprisingly good. I mean, it's not. I mean, I say we didn't tweak anything here. We didn't, but it looks good. It just means that the phase structure of the gas and the dust and distribution and so on is not crazy. Okay, in what we have simulated, and you can redshift this and see check what you can see with JWST and so on for massive star clusters. So that might be fun doing at some point. Now, the last few minutes. I would like to show you what we're currently working on. So we think we have improved the model. So we don't use dynamical delay star formation anymore. When gas crosses the density threshold, we say this is going to be a star. We wait for a free fall time, and then we sample the full IMF. Okay. It's subgrid, but we try to do the best we can for the subgrid prescription. So in the new simulations, we have a fully sampled IMF. Natalia has coupled this with stellar evolution tracks, which go up to 500 solar masses. So why do we do this? Because we think we have a good model for globular cluster formation, but globular clusters have this weird anomalous enrichment histories, which are unexplained at the moment. And we try to see, so these metals in globular clusters probably come from very massive stars. So we would like to see whether this is a reasonable explanation. And when we realize the IMF, we check for nearby available reservoir particles to sample the massive star. So if we want to sample 100 solar massive star, and we don't have 100 solar mass available, we don't realize the star. We sample again. Okay, so we do not randomly sample the initial mass function anymore. You know, star formation simulation people say, "Oh, you are crazy," but that's what we do. Okay, and one of the nice things is of this way to implement star formation is that we kind of recover, let's say, the relation of cluster, you know, the mass of the cluster and the most massive star. So observations are the stars here. If you have a fixed ratio, you would have lines like this. Okay. So this means that you cannot, at some point, you tilt over, okay? And we see some indications for this, okay? With the star formation prescription we have here. We also sample different initial mass functions depending on where we are in the you know, it's very early to talk about this, but to talk about the implications of this, but we think we have a handle on, you know, how do we make the clusters and how do we put in the most massive stars in the clusters. It does matter for the evolution of in particular, the small star clusters. Okay, then, okay, perfect. Another, like, say, sneak preview. We have, so Christian Pautmann is working on this at the moment, PhD student at MPA. So he is using this kind of simulations, and he puts in a massive black hole in the center, and the 5 solar masses. In such a simulation with the resolved interstellar medium, what I showed you before. And we use the star formation sampling with the full IMF. And we can, with this kind of simulations, track accretion flows onto the center to, well, probably sub-parsec scales. Okay, this is an example. Gas coming. So what do we want to investigate? We want to see how can massive black holes grow in low mass galaxies. Can they grow? How can they grow? So we use high resolution and try to track the flows to the center. Here's a model for feedback from the accreting black hole, because the constraints we have in dwarf galaxies is from X-rays. That's basically accretion rates. We would also try to understand nuclear star cluster formation. Okay, I say a few words. It's another question, you know, how do you form nuclear star clusters? There's this idea it's infalling sinking globular clusters, or it's in situ formation of nuclear clusters. Nuclear clusters, I think, are very relevant for galaxy evolution, possibly also for IMBH growth, different projects. And now he has included something else. And this is around the black hole. So we have done this with other, Antti Rantala has been pioneering this. Around the massive black hole, we have a region where we compute the stellar orbits with a regularization approach. It's an algorithmic regularization approach. It's very accurate. Okay. So we have sampled individual stars. We have a black hole, and we can trace, say, in this region, we can trace all the accurate orbits of all stars, including the gas distribution in the background as a perturbation. Okay, so why do we do this? We want to get an idea. I mean, there are a few interesting things that can happen here. Tidal disruption events is one. Stellar mergers is another one. Black hole mergers, intermediate mass ratio in spirals, and so on. This regularized integration has post-Newtonian corrections up to 3.5 order. And so we can track orbits of the stars. Okay. And yeah, of course, we can, in principle, trace galaxy merger, massive black hole mergers and TDEs. We do this for massive galaxies already. In low mass galaxies, the black holes don't really want to merge. That's another issue, but principle. Now here's an example of what such a simulation looks like. This is a larger cutout. This is the gas surface density, temperature, and density distribution. And this is a zoom into the center at 50 and 10 parsec. And the dots here are the stars. And there will be orange, red dots, which is massive stars, orange dots, which is stars more massive than 15, and yellow dots, stars, very massive stars, more massive than 25. And here, we remove all stars when they are older than 50 million years. So stars will disappear. Don't be surprised. This is artificial. But we trace accretion events. Here's one. Accretion to the center. And we form a stellar next event. Accretion to massive star forms, explodes, the supernova explodes, terminates the accretion flow. Okay. And I think there's another one here. Okay. So what happens is the gas is secreted into the center. We do have nuclear star. There's no AGN feedback here. We do have nuclear star formation. And the very massive star that forms basically is energetic enough, the supernova, to terminate the accretion flow. Okay. This indicates a strong competition between black hole growth and nuclear star formation on these scales. And here's another version of this movie without removing the stars. So these events might slowly but surely result in the formation of a nuclear star cluster. Okay. So you just start piling up. There's a little hole here, which is an artifact of our black hole accretion at the moment. But this is 10 to the 4 stars in the region of a few parsec. So this has qualitatively the properties of a nuclear star cluster. So there's more to be done here. Also, these simulations then become, okay, the regularization is efficient, but the efficiency breaks down in 10 to the 4 particles or so. So now we are in the next problematic phase of code development. And Antti Rantala is currently working on coupling this with a 4th order integration scheme, a forward integration scheme. This is a bit more technical. So conclusions. Oh, sorry about that. I'll leave the conclusions here. It's all great, and we can try to solve a number of questions in the future, but there's still a lot of limitations. So be very, yeah. Okay, thank you.
So it might be quite basic question, but how exactly do you want to how do you decide what goes off? Is this like a standard description that is we figured out, or is there a lot of room in this?
So we take, stellar evolution modeling is a different field. So we take tables from people who compute stellar tracks. So then every star with a given initial mass has a track. And then at the end of its lifetime, it's exploding. So we know the explosion time, and we know how much material, how many newly generated elements are ejected into the surrounding. So there are uncertainties there, which I cannot comment on. If you ask stellar evolution people, they say, oh, but this star clearly explodes after 10 million years, and the other person says, oh no, it's at least 15. There's an interesting thing that not all massive stars might explode as supernova. There might be little islands where the stars actually collapse directly into a black hole. There's a pair-instability pair-instability supernova tracks are included here. I didn't mention this. There's a gap in an initial mass of a star where there's no remnant of the star. You explode as a parent stability supernova. So this is a whole world in itself, which might or not impact some of the results here. I think for this simple model, where we have only single stars, we don't even have touched binary stellar evolution yet. Okay, binary stellar evolution is something which might be very relevant because it changes the lifetime the time distribution of supernovae for a stellar population. So, okay, this is yeah. There are a number of uncertainties there. I think I can say no, probably. I mean, no in the sense that we have not tested whether we can do this.
Is it the right resolution or something else?
Well, I think in principle, we have the physical conditions that would correspond to the observations, but I have not in detail checked whether this is possible because we have gas at all kinds of densities and so on. But it's actually very good. I've never thought about whether we can compare this to observations. Yeah, it's a good question. Yeah. Yeah.
In your rough analysis, I believe that the escape fraction of UV photons out of the galaxy.
No, we don't. We cannot, unfortunately, because we don't have radiation transfer. We just have a simple photoionization approach. It's another limitation of the simulations. So we have not. Yeah. Yeah. I could speculate. Of course, if we have very structured ISM, the escape fraction is higher. So but I cannot give you numbers. Okay. Yeah. It's between 0 and 1.
Yeah, the question one is a bit more like that. So if you look at the accretion rate on this massive black hole, does it follow the gravitational model?
The what? The gravitational torque?
Yeah.
So okay. So we accrete at a parsec. Okay. So the first question is, I have not compared it to the torque model. We have followed the accretion rate. We have followed the mass accretion history of the black holes. They don't grow much if we have feedback, and they should not grow much, I think, because otherwise, dwarf galaxies would grow their black holes, which they don't. But we have not compared to the gravitational torque model, which would be a larger scale grid model in our case. Yeah.
But I think it's interesting that it was defined on it's like the scale is like a contract, which was, and I think the way that we presented this was that we should apply to scale for 100 parsecs or even smaller and parsecs, and you have the resolution.
Yeah. Yeah.
So that question was.
So I can just say how we accrete. It's very simple. So if a particle comes closer than a parsec, we check whether its angular momentum is smaller than the circular orbit, and whether it justifies the boundary criterion. Then we put it on a subgrid accretion disk and let it move in with a viscous time scale. That's what we do at the moment, which is not a good model. Okay, it's what we have at the moment, and Christian will publish it, but it creates problems. Okay. And anyway, it's not a good advertisement, I think. Sorry, Christian. He's amazing. and he convinced me basically that this is not a good model. Okay. We have to think about something else. Yeah.
I have less expert question. So I was really amazed by your movie of the star clusters that's emerging, and I was like, wait, this is a stellar cluster. It looks just like a galaxy cluster, right? It's just, of course, many of them magnificent or more of the and lower in stellar mass. I was wondering, therefore, so what about black holes in star clusters? So if you had, let's say, this would probably be a stellar black hole at that point, right? What would their
Okay, first question. It looks like a galaxy cluster, but it's very different because galaxy clusters grow on the longest cosmic timescales, and this grows on an extremely short timescale. So but of course it's gravitational collapse in some sense. But it's hierarchical. I mean, the point is it's in hierarchical formation. So lower mass clusters don't form hierarchically, okay? They form in a filament or in a crossing of a cloud filament, but not by bringing in. So you have to meet special conditions. That's also you need special conditions. You need converging gas flows at a very high rate, okay? You form 10 to the 6 stars in 10 to the 6 years. That's a solar mass per year in a parsec region, okay? So you have to bring in, and like 80%, 70% of the gas you bring in doesn't make a star, okay? So we bring in 2 or 3 times the gas into this region, and not all of it is converted into the star cluster, okay? So you need special conditions to do this. Low shear, strong converging flows. Yes. So on the black hole question, so Francesco Rizzotto, another PhD student, has published a few papers, but other colleagues as well, a few papers looking at the early evolution of a very dense star cluster, and you can form intermediate mass black holes. Different code, N-body 6 code. So the pathways are, you can collide stars, you can form massive stars, which can then directly collapse into a black hole. You can form stellar mass black holes, which can collide with another star, accrete material, grow, and then collide with whatever, okay? Another black hole, make a gravitational wave event. He has looked at the gravitational event mass ratios and compared to LIGO, Virgo observations, and they look reasonable. Okay, we even create like mergers in the pair instability mass gap. So that's why I'm so fascinated by these objects. They could be very, very important. Neutron star mergers is another thing. Okay. Neutron stars mergers are probably the only process making very heavy elements in the universe. So where, if not there? Okay, it's a riddle. Now, at the moment, these two fields are still kind of disconnected because we do the cluster experiments with high accurate N-body simulations, no gas at the moment. This is low accuracy, but we get the environment. But I hope at some point, we can combine this.
Yeah, I was amazed to see the simulations you showed of the Northern cluster formation. Eventually Northern cluster. Does it help you explain the age and the radial distributions that you see about it? Can you get some insight into what could explain this?
I think the ages are okay. Because we have formation times which are short, which is consistent roughly with the old idea that globular clusters are single-age stellar populations. The radial distribution and so on is also okay. Now, of course, we would have to show that this happens in a cosmological context pre-realization. This is what we're trying now with cosmological zoom simulations, which is a nightmare. Okay, but What we cannot reproduce at the moment is the anomalous. So the globular clusters, I mean, maybe most of you know, globular clusters have relatively homogeneous iron distribution, but they have anomalous distribution of elements which are generated in the CNO cycle burning phase. Okay, sodium, magnesium, aluminum, and so on, which indicates that there are at least two populations. Okay, very probably the same age, but two populations: pristine population one and an enriched population. And for massive globular clusters, this enriched population even seems to dominate. And this is what Natalia is working on at the moment. That's why we have massive stars and so on. So processes, stellar evolution, which gives you a high fraction of CNO cycle elements. But those then you have to include in the second population on a timescale of 10, 15 million years. It does not completely work out. There's a mass budget problem, so you don't have enough of these enriched elements. And so on and so on. Okay, so I think it's a good model in principle. In detail, we cannot explain all the properties of globular clusters yet. Yeah.
I'll ask you one, since
I think it's from my side. I have a question more from looking at the work from far. I really like this overview on the impact on the ISM structure and where stars form and go off, based on the different mechanisms that I wonder if you have an effect on the structure, not of the ISM itself, but on the structure of the stellar component on the hemisphere. Because I know it's a different simulation, but previous slides you showed, I was a bit puzzled by the structure of the stellar density. And I was expecting something less structure. Comments on what the impact on the structure?
Yeah, that's a very good observation. So the one on the top right, okay. So what I think happens is most stars form in clusters. Initially, it's very clustered. These clusters dissolve on a time scale of 90% dissolve on a time scale of 10, 15 million years. The rest of the 90% dissolve on a time scale of 10 to 7 years and so on. Okay. So what happens is you form a cluster, it's destroyed in the tidal field, and it joins the so you see some indication. You see these clusters get elongated, they get stripped. Okay, and then they join the sea of I think this is correct. I mean, this is not correct. This is not a good simulation, but in principle, this is correct. This is what happens. Okay, you form a compact cluster. It relaxes. The low mass stars go to large radii. It's stripped, and then it's dissolved. And then if you wait long enough, this becomes a homogeneous looking distribution with internal phase structure. Okay, this is what we see in the Milky Way. Star-forming regions or disrupted clusters in the Milky Way. I think this is what happens when we don't capture all of this, but qualitatively, this is what should happen when you have star formation in disks. I think the structured appearance is correct. Yeah. Shear is important. Yeah. Tidal field is important. Shear is important. This is a dark matter-dominated galaxy model. Qualitatively, I think this is what happens in the Milky Way as well.